Oh, gotcha. All right, so we had already done some of this, but not all of it. So let's go ahead. Oh, by the way, acid-base titrations. Just a reminder that when we use a indicator, and you just had to do that on your homework, ethyl blue or phenolphthalein or methyl orange or whatever. When those change colors, that's the their endpoint. The equivalence point is when moles of acid equals moles of base, and so that was like the idea behind your homework. You got moles of one, you knew the moles of the other one had to be equal, then you took the moles and divided by liters of solution that you started with, and that was it. That was your whole homework. Anyway, we had already talked about strong acid, strong base, which was, you know, your homework and the quiz. And we had already done all this. The net ionic is always one hydrogen plus one hydroxide gives you water. And so when you were doing your quiz and it was talking about barium hydroxide or whatever, this is still the net ionic equation. You take care of the fact that there are two hydroxides and 1 mole of barium hydroxide at the bottom when you convert from hydroxide back to barium hydroxide. So what I mean by that is, if you're doing this math and you have your little table, and you get, if you get this as 4, and that has to be 4. I don't care what, if there's 2 hydroxides or not. But like if I get 4 moles of the linchpin, as I sit there and grade your papers, I haven't started yet, but I'm having a psychic vision of what's going to go down. The thing is, if you solve in your table as you 4 moles of hydroxide, then you better say that and we're talking about barium hydroxide, there are 2 moles of hydroxide and 1 barium hydroxide. You should do this anyway, even if it's 1 to 1, and I told you that over and over and over and over again last week, and that's why I told you. I told you that. So that's 2 moles of barium hydroxide. You should do that anyway, because when you go to find molarity, it asks for the molarities of barium hydroxide. And if you leave it as hydroxide, you kind of halfway did it anyway. So, moving on. Off my soapbox. I hope that worked out well for you. I hope it did. We already went through this, and you guys were fine with finding the pH of a strong acid. You're like, yeah, push the buttons, what? And then we, did our little charts, and we added it all together, and we found the pH. This was fine, no problems. We already went through this. Keep it on going. So, looking at the titration curve, you can look at a titration curve and you can tell you're talking about a strong acid starting out. Like this is obviously an acid that you started with. If it starts up here and it goes down, then you're titrating a base with an acid. So that's how you can tell. Yeah, I mean, the graph on the homework, that was cute and everything, but you can pretty much do it in your head, hopefully. If the pH is, 1, 0, something like that, then you know it's a strong acid. If the pH is starting 2, 3, 4, then you know you're starting with a weak acid. That's a big key. Also, when you're dealing with a weak acid, because you're starting up here, it will kind of look flattened out. And we'll see that here in a second. But if you have a strong acid, strong base, it doesn't matter the molarity of each of them. It doesn't matter. The pH at equivalence will always be 7 because you'll only be left with the conjugate acid and a conjugate base of a strong acid and base. Ringing the bells? I'm trying to ring bells right now. I'm not trying to teach anything new yet. Still large pH change at equivalence. We had already, I feel like we already did this one. So that was fun. Y'all had fun. You were fine with this. On your homework that you're going to do here in a second, sometimes we have older solutions in the lab, and you'll standardize solutions using a powder, an ionic compound. Let me explain that to you. This potassium, and I forget the name of this ion, but it's really common to standardize sodium hydroxide with. Here when you go to do your homework, when you look at this, this is your acid. That potassium is going to be a spectator ion. And so when this reaction, if I go ahead and write it down, you can see that potassium, here it is, this is the hydrogen that is left. And to me, to be honest with you, I'm pretty sure that is a spectator anyway. So it's not going to matter. but you basically have HC8H4O4, and then this is your conjugate base. You can throw that potassium off if you want. But this is one of the formulas in your homework, so you can refer back to here if you want. But sometimes your acid-base titration won't be with two liquids. Like they'll happen in an aqueous solution. They'll happen in water, yeah. But you can start with a solid. And so if you're asked to start with a solid, can you take this grams and can you go to moles? Yeah. And so I don't want to add it up. Do y'all want to add it up? Yeah, me neither. But we're going to have grams to moles, and that's a simple one-step conversion. So I'm going to show you this one real quick. So there's the molar mass. I don't want to add it up. And that's my number of moles. And so if this is this at endpoint? Yeah, so at equivalence, that would also be my moles of hydroxide, right? And so what you should do, this is the best thing to do, is say that equals moles of hydroxide, and then do a step that is, 1 mole of hydroxide is 1 mole of sodium hydroxide. And if you don't feel like doing 3 more seconds of work, then I hope you feel like doing a whole other semester of college chemistry, because you have to understand that if you get a 4 on this test, you get 1 semester. If you get a 5, you get 2. And some people will be close. And same thing with a 3 and a 4, depending on your college. It's worth it. It's worth it to do this step because sometimes you'll have those group 2 bases. Anyway, so that's my moles also of sodium hydroxide. So 1.540 times 10 to the -2 moles. This is what you just did on your quiz. And then I'm going to divide it by the liters there. So 0.04255 liters. And then, of course, that's molarity. Right, so that shouldn't blow your mind. You just had to take a quiz on this. Are you okay? I just wanted to show you that sometimes, you do start with a solid. That's fine. When in doubt, mull it out, put it on ice, check the formula sheet twice. So, and that's what they just did, and they divided it. So, on Friday, the only thing that I had done in second period that I didn't do with you was this example problem. So let's just go ahead and knock it out real quick. It says the titrant from the previous example. Actually, I skipped this one. That's a lie. I'm a liar. The one that I did with them was example 3. So I'm going to go ahead and do that. So this is the one that I did with them that I didn't do with you. So a 30 milliliter sample of 0.5 molar acetic acid is titrated with 0.5 molar sodium hydroxide. Determine the volume of 0.5 molar sodium hydroxide that must be delivered to reach the half equivalence point. So when you're doing half equivalence point, we won't have half the moles needed. So I'm just going to hide this with my little white box, and then we're going to just work it out right here. My little white box has a black line now that my pen's broken, but that's okay. If you get tired of doing these BCA tables, there's some shortcut ways to do it. I thought it was funny that the people that were doing the shortcut way, because they Googled it, they did terrible on their quiz, and then they didn't have any conceptual understanding during the homework. So please just do it my way. Thanks, I love you. Anyway, HC2H3O2, since it's a weak acid, when I do my net ionic, I do have to keep it together. And then I have hydroxide, and then that gives me water and acetate. So to start this out, I don't know the volume, obviously, of sodium hydroxide. That's what I'm looking for. But I do know the volume of the acid. So I have 30 milliliters, which is 0.03 liters. I'm just doing it right here because I don't have room. This is obviously not part of my table. I'm just going to find moles of acid real quick. Are you okay?
I'm not crying over this. I just couldn't see you.
I'm sorry. I was just like, that looks terrible. I'm really sorry. And then the molarity is 0.5 moles in 1 liter. And then this is the acid I'm going to run out of room, H3O2. And then I am going to take a second to go 1 mole of HC2H3O2 is 1 mole of hydrogen. And the reason I did that is because, oh, I didn't even need to do that. same. On your quiz, you know, on that second one, you had to go put it back into the table. I hope you took the time. Like, wait a minute, this is 2 moles of that, right? Yeah, okay. Anyway, so when I multiply that together, I guess you get, is it 0.015? Do the math, 0.015. Yeah, is that right? Okay. So that's that many moles, and then at half equivalence, we will want to have half of that number in hydroxide. So that's 0.0075. So you can just go 0.015 divided by 2, and you get that. So just to confirm, minus x, this should give me 0, and then I should be left with 0.0075, and I am, and you can see that that half was neutralized. Anyway, that's my moles there. What were you? I just multiplied 0.03 times 0.5. Is that? No, you're good. So anyway, I need 0.0075 moles of hydroxide. And so if I have molarity, right, and then I kind of need to, I can't erase anything. I can erase everything. That's all I can do. I just needed some room. There we go. That makes me feel better. And then what is when I have molarity, right? You can use molarity as a conversion factor, and you've been doing that, but most of the time you use molarity as a conversion factor, it's moles over liters, but surely you can also flip it upside down. So 1 liter is also 0.50 moles. And that's how you're going to do these volume units. Okay? Then this is going to give us the answer in liters. So you know, if you want to go to milliliters, you will have to divide it, but 0.0075. This was throwing a lot of people off last period, but y'all are smart. And that's 15 milliliters. And you know, okay, they had the same molarity. You start out with 30 of the acid, so the answer should be 15. That's cute. Yeah, you should have been able to do this in your head, but you have to show the math. Because it's always like, provide a calculation and justification, and plus they're not looking about this even, right? So that's the first part. Are you okay with that? And then I'm sad that I didn't do it. Can I renege? Back up. Oh, I should have done it over here. But like 1 hydroxide is 1 sodium hydroxide, and then, yeah, okay. So that's a mess, but 15 milliliters it is. The pH at half equivalence point is measured to be 4.74. Find the pKa. Is there something special about mid-equivalence point? Is pH equal pKa? Yeah, okay, I'm not doing anything with that. But just for fun, if you wanted to see it, pH is equal to pKa plus the log of the conjugate base and the acid. And at halfway equivalence point, these are equal. So that's 1, and then the log of 1 is 0. Identify the main species that are present in solution at half equivalence point. At half equivalence point, I would have still some acid left. I would have some of the acid neutralized. And then I guess I would have some sodium. The tricky part with a half equivalence point is that, you know, you're not going to have any hydroxide. If I'm titrating with a base, all the hydroxide will be used to make water. If I'm titrating with an acid, all the hydrogens from the acid will be used. So you're not going to have any, hydroxides, because all the hydroxides came in and took this hydrogen and made water. Okay. Sure. You want me to draw? I'll draw it. I actually drew that at the beginning of class, so I already drew it. I'll draw it again. Alright, so there's that. Good times. So that pretty much catches y'all up to second period on Friday. That's what we did. So there's that. And then that's what's in solution. I don't know. As far as them having hydronium, that's not a major species at this point, but you have to, I wouldn't put that. But to some extent, to some very small extent, there's a little bit of ionization. I don't like that. I don't do that. It's wrong. No. Were you following me? Don't worry about it. And when they do their answer key, you need to pay attention. I'll tell you some stuff they got messed up. All right, so this is what I was telling you about a weak acid and when we titrate it. Notice the beginning pH is above 1 or 0. It's like 4, 3, 4, 5, something like that. I mean, I can obviously read that as 4, but yeah. The equivalence point would be in the basic range would be above 7 because the conjugate base of that weak acid is going to be strong enough to pull the pH above 7. This is only true for monoprotic weak acids. And so if I have a polyprotic weak acid, like phosphoric acid, yeah, my beginning pH will be around 2, and you'll have an equivalence point. Can I just drop for you? When I go to the next slide and you see what they drew, you might have a panic attack. So let me just do it for you. Okay, great. So if I titrate, if I add that to phosphoric acid, at the beginning, the pH, and I'm eyeballing this. I mean, I'm not going to be dead on. I'll have it memorized, and it's not important that I have it memorized. The concepts are what's important. I kind of, there we go. Good thing I'm tall. But the beginning pH of phosphoric acid, which is H3PO4, I'm starting with that. How many protons does this have to? 3. Okay, you ready? Ha! So that first one, it starts around maybe like 2-ish. And it's kind of slopey. The weak acids kind of have a little bit of slope to it, and you have an equivalence point around about there, and it flattens off. So that's the first titration. And here, after equivalence, I'd be left with H2PO4, 1 minus. And so there. And then, check this out. The pKa, the Ka, right, there was like K1, K2, K3, when you have more than one proton. The pKa1 of this one would be, you know, somewhere around 2. How do you feel about that? You okay? Well, if I keep adding sodium hydroxide, I'm just going to this actually should be flatter. Hit my back button. Should be kind of flatter. So now I have another equivalence point. And then after that equivalence point, I'll be left with HPO4, 2 minus. Okay. And then I'll have another equivalence point. It'll be even flatter. And I should have went up more. I don't care. I'll be left with just PO4. So this is the pKa of H2PO4. This would be the pKa of HPO4. And so on the AP exam, if you're asked about these polyprotic acids, you can look at how many up and down equivalence points are on to tell how many hydrogens are. So there's 1, 2, 3. Let me go there. So I could tell from this graph that this acid had 3 hydrogens. 1, 2, 3, because there's 3 equivalence points. That's how you can, like, because they look crazy. Like, what am I looking at? That's how you can tell. And then they might ask you about the Ka values. Now, check this out. It's kind of cool. Remember that pKa is a measurement of acid strength, and the higher the pKa, the weaker the acid, right? Well, the pKa of, you know, this, well, that's not an acid, I was just kidding. The pKa of this one, I mean, I didn't draw it that great, would be like 9, and this is the weakest acid. And this one would be like 6, and this one would be like 2. And so mathematically, you can prove that in the titration graph. Isn't that nice? And then, of course, you could take this data, the pKa here, and take the negative log and do all that, and you can get to Ka. Then you can do, like, some math. You don't have to do a lot of math for these polyprotic ones, so it's more concept-based. Are you okay with that? So I couldn't draw my board on Friday. That's why I didn't even attempt to teach this. Well, this is not happening, right? Like, how am I going to try to explain that without drawing it? So the next line, still large change in pH. This is the buffering region here, just where bufferings happen because you have that conjugate base and the acid still present. So this would be something like a polyprotic acid. This would be something like maybe sulfuric acid. You know, I could tell it's sulfuric acid. How many hydrogens did it have? 2. See, so if they gave you this graph and they said which acid could this be, then you have to look for the one with 2 hydrogens. That's the kind of question you would have. You wouldn't have to do math for this necessarily. Okay. So this would be sulfuric acid, and sulfuric acid is a weak acid, so maybe that's not the best choice, but something like hypochloric acid, H. No, that wouldn't work. I'm trying to think of one that has 2 hydrogens. Not really coming to me right now. But some of the weird carboxylic acids, like malic acid, has 2, but you don't know what I'm talking about. Anyway, 2 hydrogens. Notice it flattens out each time because the next acid's weaker, and then the next acid would be even weaker. All right, so indicators. How does that even work? Okay, so when you did your lab, brothymal blue, it goes from yellow to blue, right? This one goes from red to purple. So don't worry so much about this. Let me make this go away. I'll make all your problems go away temporarily. Ha, 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 ha. So check it out. If I'm starting out in an acidic solution, right? If I'm starting out in a situation where, like, I put a couple drops of this into hydrochloric acid, right? So I got a bunch of H's down here. And they're really hydroniums, but this is hydrochloric acid. So the stress to this equilibrium here, by the way, acid-base indicators are weak organic acids. So they're acids themselves. That's how they work, okay? But if I put a couple drops of this purple stuff or red stuff into an acid, it's going to stay red. Look at the hydrogens off the hydrochloric acid. What way are they going to shift equilibrium towards with a common ion attack? Towards the red thing, towards the whole undissociated acid. Do you see what I'm saying? You feeling me? All right. Now, if I start titrating, so basically I have a couple red drops in hydrochloric acid. If I start titrating this with sodium hydroxide, right, what's going to end up happening? Oh, I should have made dots. I think I'm going to make dots. Let's do it. Let's just commit to the cause. It'll be fun. Oh, I'm sad I made that red. Can I make it blue? Okay, thanks. And then we'll make green just green because that's fine. If I start, here, there's 3 of them. If I start titrating this with hydroxide, that's not hydroxide, I'm not done yet. I can only do 1 dot at a time. I wonder if I could do 2 dots at a time. Probably not. Too much. I want to see if I can. Don't you want to see?
It'll be super fun.
If I can do this, the answer is no. I probably just broke it forever. I lost my train of thought. If I titrate this with 3 hydroxides, did I break anything? I'll be making water, right? So now I don't have any hydrogens. Do I? Which way is equilibrium going to shift? Toward the products, because I just created a stress to the system by reducing the amount of products, didn't I? Yeah, so guess what it's going to be now? Purple! Isn't that fun? So that's how they work. Yes. So that's how they work. And the color change, that magic little color change, because this is the acid, right? The color change, that little tipping point, it's flashing like a little neon sign because this is exciting, I guess. Or my stuff's broken, whichever one. Anyway, that magical tipping point happens right above and below where the acid and the conjugate base are like as soon as I have more conjugate base, this sucker is going to be purple. As soon as I have more acid, it's going to be red. So that's the tipping point. So you want to, here we go, here's the big idea. You want to pick an indicator whose endpoint color change is equal to the is equal to the equivalence point at of your acid base. So like strong acid, strong base is 7. I want to pick an acid base indicator whose pKa is 7 because the pH where the color change happens will be equal to 7. You feel okay about that? It's the application part of it is pretty simple. You're just given a chart and you're like, which one matches? Okay. So anyway, if I start to make the solution basic, it's going to shift equilibrium to the right to make more hydrogens because I just removed all the hydrogens with the hydroxides. I just made them into water. So we're almost done. You look so sad. So I just explained this. The color change happens where your acid and your conjugate base are about even. So what you want is you want the pH to be the pKa. And I just explained this without craziness. So this is so super chill, right? You have, and here's how the AP exam will go. You have this strong acid and this strong base. Which indicator, given the table of pKa values below, which indicator would be the best for your experiment? Oh, I don't know. How about bronchithiol blue? How about that? That's all it is. So I just explained all that. I did circles, whatever. But you want to pick the indicator whose pKa is equal to the pH of your equivalence point. So if we had a weak acid, so they may not give you like all the information. Like if you're titrating a weak acid with a strong base, so you know the the equivalence point pH was going to be higher than 7, right? Off the top of your head, you have to know that. And so like you would probably pick phenolphthalein. Then they might not have like this yellow one. They probably wouldn't have that one yet. But if you were titrating a weak base with a strong acid, you would want to pick probably methyl red. You see, you follow my logic there? Yes? Okay. So here's an example. Super hard. Equivalence point is 7. Which indicator do I want? Ooh, how about bronchithiol blue? Or, look at that. And that's where the color change happens. Magic! Would you want to use with acetic acid and they gave you the equivalence point at 9.1? Oh, how about phenolphthalein? How about that? They don't have to be exact. The reason they don't have to be exactly the same is because you have this large shift in pH, and that's a drop. And so as long as it's close, you're good. All right, how you feel? That's all your work. All right, so let's go ahead and take this answer key. What? We already did 1 through 6. There's a couple errors on here, so I want to talk about those. Thank you. Alright, so y'all already should have done, hopefully. I saw somebody last period, by the way, starting with number 1. I was like, oh, your life is going to be uncomfortable for a while because that hadn't started yet. Ha! Anyway, we already did all these. And so we stopped after number 6. And so 7's looking real good. 8 was looking good. 9 was good. 10 had an error. The error on number 10 was, maybe it was number 11. There's an error on here somewhere. I'll go back after y'all tape it and find it. I'm really sorry. Anyway, I feel like there's one. Alright, let's tape it and then I'll go back because I know there was another error. Ooh, look. This has 2 hydrogens. I don't even know what the question is. Labile means it can move. Not fun. Get removed. The error on here, on number 10, there was a, oh yeah, B should be 0.0 something. It should be half of this number, 0.0280. Half of this number's the answer. They just started doing some like random stuff. It's not right, okay? Half of that, it should be 0.0280. Okay, so B is wrong. And then on number 11, when they start talking about spectator ions and stuff, this has no hydroxide and it doesn't have hydronium. That made me mad. No, no. Okay, so there you go. You good. Have fun. Good luck. Let me know if you have any trouble. So if you need some more conceptual work, like if you're like, I don't get that simple thing, or you just don't remember everything, you might want to start with the pre-lab questions to get some conceptual work and kind of